This episode has been sponsored by PCBWay. Greeting Earthlings! If you follow the channel, you know that we got our greasy hands on an Apollo Flight Director Attitude Indicator, thanks to patron and collector Richard. It was nicknamed the 8 ball by the astronauts, or just the ball, but NASA officially called it the FDAI. Unlike two-dimensional horizon indicators found in airplanes, this space instrument is three-dimensional and indicates the spacecraft attitude as derived from the inertial platform. It is the primary flight instrument for spaceflight, telling you which way you are pointing. Richard's instrument had a storied life at NASA. It started as an Apollo LEM indicator that was used in a LEM simulator trainer. After the Apollo program, it was then slightly modified and used in a shuttle simulator. As we learned in the previous episodes, something dreadful must have happened to it, and it ended up as scrap. We opened it up and found plenty of evidence that it was used as a parts unit before being scrapped. Many screws were missing, wires were disconnected or cut, an entire Servo amplifier board was missing. In the last episode, we reconnected the wires where we think they should have been, enough to get the needles working again as well as some of the lighting. We then turned our attention to the ball itself, which uses a complicated servo control scheme for actuation, involving AC motors, tachometers, control transformers, and servo amplifier boards. We first checked the two remaining electronic servo boards and found that both were bad. They were even marked as such. Fortunately, we got 3 working replacement boards from a related ARU-11 unit from an F4 Phantom plane. But before we put the working servo boards into the FDAI, we double-checked continuity to the various motors and control transformers, just in case. And sure enough, one of the motor connections had failed. We traced the faulty connection and came to the dreadful conclusion that the fault was inside the ball. Now, all of a sudden, this is a much more difficult repair. The fault could be in the wiring, the slip ring, or the motor, all of them way inside the ball. We must perform ball surgery. Ouch, just saying it hurts already.
One motor, the center point of the windings does not seem to go to the 26 volts as it should. So either the winding in the motor is broken, or there's a bad connection somewhere.
And which axis is that?
Pitch.
And is that where the amplifier was missing?
No, the roll was the amplifier missing.
And if it's in the ball, I get to take the ball apart?
But I measured up the connector here, and so that shows that everything on this side seems to be fine. So it's either the slip ring inside the ball,
the second slip ring, or the motor itself, or a wire. So we have to open the ball to figure it out. So I looked at it under the microscope, and obviously somebody has tried to get into the ball because there's like half of the screws are missing, half of the screws for the needles are missing, half of the screw for the front shield are missing.
Hopefully we will succeed where they failed.
And my worry is about that because they had the original parts and they couldn't repair it. At least we'll confirm whether it's the slip ring or the motor. Okay, 1. And same thing, this had 4 screws and there's only 2 left out of the 4. Okay, so these are... It's written pitch, okay. Same thing, 2 screws instead of 4. This thing had been completely taken apart exactly the same way we're going to do it. Alright. It's way too long. So these are not even the right screws. This has all the trappings of a unit that has been monkeyed with and left to die. Hopla. Oh, and now, they shouldn't do that. This has also been...
So what's holding that in place?
Well, a screw that's loose. So this thing is also missing its screw.
Yeah, that screw looks exceedingly stripped.
Yes, this is a stripped screw. Alright, so
Which maybe is why those back screws are
Yep,
loose.
yep, exactly. I think we just found out why. No?
No, that's not holding it. I think, unless there's one buried,
It's buried.
under here.
I see one here. I have access to one over here. Now I have access to the hidden screw, which should have been tightened and is not. It was completely loose. Alright. Okay, let me think for a second here. So yeah, so that's what you should get the flag out, right? You shouldn't have to do this. But this
Yeah, that.
technician from hell has struck here again, so that screw is just stripped. No screw here. 3 out of 6, okay.
Or 3 out of 8 even.
Alright. And see, there is an extra thingy here, which oh, it's for the roll. So if you look at the bezel, it's going to mark this. It's going to be a little arrow that goes around as you roll.
Okay.
So I have to remove that. Okay, well, it's loose. Guess what? Oh man.
Don't drop it inside the ball.
Okay. It's loose too. Okay. Somebody with gloves can hold that ball steady for me. There we go. Hop. Okay. So now comes the ball removal thing, and that's where I use my special wrench, which is probably still over there. Okay, so I took a look at the microscope, and it's different from the ARU11. Again, they have a single screw, and it's a Bristol wrench. It was very stripped, but I still could grab it. Yeah, it grabs. Okay, here's the grub screw. Here is your dream come true. That is loose, but the ball is not loose.
You need the combination.
You can see that one has marks. So somebody has tried to pop those open with less care. Okay, in order to do that, I have to be seated and in front of the camera.
Moments later.
Okay, so we have our first ball off. It just slides off. And then I was wondering why this thing moved, and it's because it's not tightened up properly. Same problem. So it had been disassembled. You wouldn't need to remove that unless you wanted to go and look at the motors.
Mm-hmm.
And then after the guy had done that, he said it was just not worth screwing back together. Okay, so now
I think it should actually just come off with a linear pull.
no, I can hold up the shaft.
Yeah.
So I can take it off. It's going. There we go. Up. All right. Oh.
More connectors.
Okay, Ken.
Okay.
Dream come true over here, but it has been monkeyed with.
So do you want to label which hemisphere came off which side?
Yeah. It's cracked. No, it's not cracked. It's okay. All right. So that's the one you are going to want to check. They are connectorized on this unit, which they weren't on the ARU11, I think, right? Alright, it's now obvious that this was a hand-modified unit for simulator use. They had to replace the inside of the ball, most likely because the Apollo LEM used resolver control transformers, but they needed instead the more standard synchro control transformers, 3 windings instead of 2. So they spliced back a traditional synchro mechanism in there with hand-glued connectors for reattaching the wiring. Not pretty, but it did the trick for the required job on the ground. We just caught NASA trying to save you some money.
And the same on on the yoke, there's a connector rather than
Yeah, then continuous.
soldered.
Then you have all your wires that are, so then there's there should be 2 pairs.
Right.
This is whatever, one is pitch, one is yaw, so this pair here, motor, position sensor, control transformer, and then there should be another pair somewhere here. That will do in the other rotation, and this is the motor and the control transformer. Oh, this is the counterweight. Oh, this is the one that was missing from it. This is why our RU11 was imbalanced. It was missing the counterweight. Remember, it didn't have it?
Yeah, we should have taken it to a tire balancing shop.
Yeah. I'm just looking at the slip rings, and they look fine with from my old eyes. This is fine. And the other one is harder to see, but I don't see anything bent.
A few moments later.
I left Master Ken alone just for 5 minutes with the beast, and you found the problem already?
Yep, there's a broken wire right here.
Oh, and is it exactly the one you thought it would be?
Well, it's connected to both motors, so it's probably the center tap connection to them.
Okay.
So sorted that together and we're ready to go. Probably take me a few minutes to
Just confirm. Well,
confirm,
anyhow, it has to be attached, but
yeah, obviously it should not be
detached.
detached.
And while Master Ken is figuring out the wiring, since we had taken that off, I decided to replace the lamps. Half of them were not working, but now they're all doing it, so that's how it works. There are little PCBs on the back. Soldered in. And they are weird lights. They have the little blue condom, and it's actually glued in, so I can't remove them. So I just went with bare bulbs. And also we noticed, if you look at this one at the back, you can see the writing. And from the back you can see the original writing that had been overpainted. We can confirm that that was indeed a real Apollo LEM FDAI, reused for the shuttle program to save some money. These were expensive, even for NASA. Pitch rate. And this one says roll rate. So definitely a former LEM thing that was used for something else. Anyhow, it lights up now. Okay, just for the good of science, I finally managed to find capacitors that are new old stock but don't leak. I'll put one of the new old capacitors, and you test them for leakage at 25 volts, and you have to wait that it charges up, but eventually it opens up. So that is a good capacitor. So right now the performance of this amp is doubtful. I have the green output is correct, the blue is way too late, which I think has to do with the first stage of amplification. So let's change the caps in the first stage. Yeah, got that. Okay, I can pick it up from its epoxy. Got it. Okay, testing the cap that I just removed, and my guess is that it's very leaky. And it's leaky. Doesn't open up. All right. Yeah, as far as capacitance is concerned, 6.8, which is what it should be. So it's just a leak problem. So let me put a new old one. Let's see if it makes a difference. Turn power supplies on. Oh, it made half of a difference here. The amp would probably work like this. It's a little bit imbalanced, but I never saw them balanced completely. So as we saw in the previous episode, the imbalance is from my test setup. So the amp is repaired. I replaced all the other mil-spec wet tantalum caps where I was at it since I had the original exact parts. And I checked the last cap and it didn't leak, it was perfectly good. So this is as good as it's gonna get. This one's repaired. This one similarly looks like up. Not as bad as the other ones though. The second FDAI Servo amp also showed signs of weakness, so it got the same cap replacement treatment. Okay, I also recapped this one and I measured the caps and none of them was particularly bad. Oh, there you go. Okay, that looks correct. A recap helped and those tantalums become leaky. They don't lose capacitance, they just become leaky.
Meanwhile,
Eric, you got something new. You've been hard at designing.
Yes, hard at work designing. So
Hey, PCB way.
order in from PCBWay. We have our FDAI driver board, and then that drives the synchros for yaw, pitch, and roll.
And then you have a bunch of pots for the needles and everything.
And
That's the
that'll
top.
let us control all the axes and the needles, so it's got little drivers in here that will run the analog panel meters inside the instrument.
Oh, my FRAM board is for the MMD one.
That's right.
32K of RAM, yay!
Of FRAM.
Of FRAM.
Non-volatile
All right.
FRAM.
And that's for the Computer History Museum.
This is for the 1401, which has those 729 tape units, like the ones that you've been doing the clutch jobs for.
Yeah.
But this emulates an entire set of drives on a single board.
All right, that's a cool set of boards.
3 weeks later.
So it's a few weeks later, and Eric has been hard at work, and you have done a good job with your boards. This bad boy here, which you made to drive the FDAI, and for one synchro axis is 3 outputs of 400 hertz.
That's right.
Right.
3-phase, 120 degrees apart,
Right.
variable amplitude.
And then Ken was on the software side of the thing. Can show what we should look at, which is really the synchro
So you
here.
should look at the synchro. I put a little bit of blue tape on here so you can see the
Right. So the synchro represents one of the axes of the FDAI ball, right?
That's right.
Yeah, we just want to hook it up to the synchro before we to make sure it works before we hook it up to the
You don't
FDAI.
want to fry the
Just
FDAI.
in case.
Can you explain the signals on the scope?
This is our 400 hertz power that's going to the synchro, and then we're generating 3 400 hertz signals that are synchronized to the input power. And these are generated by high frequency PWM. So the TNC is actually generating sine curves to create these signals. So these are like totally synthesized sine waves.
So first hook up attempt.
First hookup attempt.
I put the thing back together, except for the outer envelope.
So you ready?
How to fly it.
So
Yeah,
it did
move.
deflect. Oh,
There you go. All right,
Nice.
we have action.
Let's do pitch rate.
Okay, yeah,
Okay.
it moved.
It was the wrong one that moved, wasn't it?
Yeah, there's some signals aren't going through correctly. Oh,
Yeah, you roll.
And this one's going to be a little bit more interesting because we also need 115 volts.
It's moving, but...
Roll.
Oh, because the other one is not connected. When it's not connected,
correct.
they go free. Okay, so you have control over one. Excellent.
Let's do pitch.
Aha. Oh.
Ooh,
We have FDI action. That's pretty cool.
Look how quickly that moves.
Uh-huh. Well, that is the servo amplifier that we repaired.
Give it some big rotations.
All right,
Okay.
but that's it. We have an FDI that works.
Very twitchy.
So
That sounds grindy.
yeah. Okay, so now with improved Arduino control.
I made some code so it should just sort of go through nice slow loops.
Ooh.
Stop!
Thank you.
Oh!
I guess your code wasn't quite right.
I guess your board wasn't quite right.
We are not immune to regular electronic development disasters, which degenerate into the usual software versus hardware finger pointing. Turns out the Class D digital driver that Eric designed is very small and efficient, but it is fragile. You have to drive it perfectly with the correct software-defined pulses. To Ken's defense, it was not his fault either, but a bug in the library, so we'll point the finger in a third direction. And Richard is back to inspect his newly repaired FDAI, and you have your latest version of the software.
Yeah,
So if it doesn't behave correctly, we will blame the software.
right.
Okay. It's flying. So Ken made a program that displays an actual aerobatic RC flight into the FDAI. It's just one of the very few flight data files that we could find off the web. Well, it works much better. Well, Richard, it looks like your LEM FDAI has been repaired. That was quite an adventure. Thanks for the loan of this rare instrument, and next time if you bring us a broken LEM and a moon, we'll try to make them both work for a landing. In the meantime, see you in the next episode.